We're now going to cover the iterator pattern. In addition to understanding how the iterator pattern works in general, we're also going to teach you how to recognize how the iterator pattern can be applied to access all nodes in an expression tree flexibly and extensively. The purpose of applying this pattern is to create objects that traverse the composite-based expression tree and access each of its elements one at a time. Iterator decouples the expression tree traversal and the way in which that traversal is used from the internal structure that uses to implement its internal composite-based representation. Let's talk a bit about the context in which this pattern is useful in the expression tree processing app. Several user operations require accessing all nodes in an expression tree. For example, the print operation is used to print the current input expression using the designated traversal order, in order, post order, pre-order, and so on. Likewise, the eval operation is used to evaluate the value of the current input expression, to print out its yield. If we were to do things incorrectly, we might be tempted to hard code the traversal logic into the expression tree itself. For example, we might add a traverse method to the interface of expression tree. But this approach would have a number of downsides. For one thing, only one traversal would be allowed at a time. Likewise, it's also hard with this model to control where and when to stop the traversal. It might be tempting to just let it traverse the entire tree all the time, even if that might be overkill. Another issue is that having a client explicitly traverse an expression tree via its internal links will impede usability and extensibility. For example, if a user tried to write a recursive function that took advantage of the fact that each expression tree had a left field and a right field, that would break if we were to modify the expression tree to handle other kinds of nodes, such as a ternary node, which would have yet another child. So we'd like to find a way to not expose this kind of information to the application code. What's our solution? Well, we're going to end up encapsulating traversal as an object. And we'll do this in a couple of steps. First, we'll create an iterator object that encapsulates expression tree traversal without requiring clients to know how it's structured internally. That way we could go ahead and traverse the tree, take a look at its values without knowing how it was implemented. Here's an example of a pre-order traversal of the expression tree -5 times 3 plus 4. When we do pre-order traversal, we print the node the first time we visit it in essentially a depth-first search through the tree. So we print off the multiplication symbol, print off the minus sign, print off the value 5, print off the plus sign, print off the value 3, print off the value 4. That's an example of a pre-order traversal, but it doesn't expose how the tree is implemented. It just provides you with the results of doing the traversal. Next, we'll go ahead and define methods to create an iterator, check to see if the iterator is finished, and access each element if it's not finished. The code we show here illustrates how we can have a factory method, such as make iterator on an expression tree, return an iterator, which is part of the Java JDK Iterator interface, and then have some methods to be able to check to see whether the iteration is done, and if not, access each element one at a time to do something with it. As mentioned before, we're actually going to use Java's Iterator interface as the basis for our iteration in the expression tree. Java defines a generic interface for traversing an aggregate data structure called Iterator, and it has a number of predefined methods. These are virtual methods that you have to subclass or implement with an implementation class. The hasNext method returns true if there are more elements in the iterator. In other words, it's not finished. The next method returns the next element in the iterator, assuming it's not finished. And the remove method can be used to remove an element from the underlying aggregate itself. There's more documentation you can find at the Java website to learn more about this interface. From a commonality and variability point of view, we have a common interface we use for expression tree iterators that conform to the Java Iterator interface. And from a variability point of view, we can come along and specialize different implementations of these iterators via some kind of creational pattern. The way in which these various pieces are put together conforms to the Gang of 4 iterator pattern. The intent of the iterator pattern is to access elements of an aggregate without exposing its representation. You should consider applying this pattern if a number of these different conditions hold. If you require multiple traversal algorithms over an aggregate, we might want to go through it in different traversal orders, for example. If you require a uniform traversal interface over different aggregates. In our particular example, we're primarily working on expression trees. But more generally, you might want to have a way to traverse lots of different kinds of aggregates or containers. trees, sets, maps, queues, lists, and so on. And finally, if you have aggregate classes and traversal algorithm or algorithms that have to vary independently, you want to be able to keep those things independent of each other so they can mix and match in various different sequences. Here's a diagram that illustrates the structure and participants in the Gang of Four iterator pattern and also maps them to how we're using them in our expression tree processing app. There's something called an aggregate, which is essentially a container where the actual information is stored that we want to iterate over. There's also a factory method called createIterator that makes an iterator. In our case, this is the expression tree class, which has a makeIterator method that creates the iterator. There's also an iterator base class or base interface, which in our case is Java's Iterator Interface. And this defines a number of methods for being able to traverse through each element in the aggregate one at a time. Then there's a number of one or more concrete iterators, things like pre-order iterator in our case and other variants of that. And finally, in some realizations of the pattern, there's also something called the concrete aggregate, which inherits from aggregate and then decides how it's going to create the appropriate iterator. We don't use this particular form in the expression tree processing app, but it's a very common approach. You'll see how we end up using it when we get to the implementation section in just a moment. Here's an example of how we could implement and apply the iterator pattern in Java. We're going to use a stack to implement a pre-order traversal algorithm for going through each element in our expression tree one at a time. We'll also talk about other iterator implementations later when we get to the strategy pattern. Pre-order iterator implements the Iterator interface parameterized with the expression tree, and we also maintain a stack of expression trees that we'll use to emulate the recursion using an iterative approach. When the constructor is called, it takes a base pointer or a root pointer to the base of an expression tree, and it goes ahead and it puts that expression tree onto the stack. So now there's at least one element on there. The hasNext method checks to see whether or not the stack is empty. If the stack is empty, then hasNext returns false. If the stack is not empty, then hasNext returns true. Here's an example of the next method. This is used to advance the iterator, to move it onto the next element and return what was currently there. In our particular implementation, since we're using this as a stack to simulate recursion, we're going to make a copy of the top element on the stack, which will return as the result of next. And then if there's any left or right children, we'll go ahead and push them onto the stack after first popping off the element that was top before. And that's how we go ahead and advance one at a time. This is an example of how we create an iterator. We implement a makeIterator factory method and put it in the expression tree class and use it to return a new pre-order iterator. As you can see here, when makeIterator is called, it goes ahead and creates a new pre-order iterator, giving itself as the parameter. The pre-order iterator constructor will know to push that particular expression tree item onto the stack. This is an example of the factory method pattern. We're actually going to see our expression tree processing app does a little variation of this, but this will give you an idea to get started with at this point. Here's how we could actually use pre-order iterator to print the contents of an expression tree in pre-order. And what we're going to do here is also illustrate a couple other interesting aspects of how you might use iterators. As you can see, we start out by calling the makeIterator factory method on expression tree, and then while there's something left to iterate over, we take each element one at a time, and we do a type-safe downcast to check to see whether the element we just got back is in fact a leaf node or a composite node. If it turns out that what we got back is a composite node, which is what it would be to start out with, because it would start out by getting the multiplication symbol that was part of the tree, then we're going to go ahead and downcast the item to be a character, and we'll print its result out. So it would print the multiplication symbol in this case. Likewise, when we print out the minus sign, same thing happens. It's actually a composite node, not a leaf node, so it chooses that. When it gets to the number 5, however, this is in fact a leaf node, and so now when we do the type-safe downcast, we realize it's a leaf node, so we print this out as an integer. We cast it to int, so it prints out properly. The plus sign is another composite node, so that prints out the plus sign. And then the 3 and the 4 are both leaf nodes, and those get printed out appropriately as well. Later on, in just a couple of videos, we'll show how we can use the visitor pattern to eliminate the use of these expensive and somewhat error-prone downcasts. Let's take a look now and switch over to the editor, and I'll show some examples of how we implement the iterator pattern in our Java application. Our iterator pattern implementation appears in a number of different places. This particular discussion will just focus on one implementation of the iterator pattern. This will be pre-order iterator, which is of course in the pre-order iterator.java file. If you take a look at this implementation, you can see that pre-order iterator implements the Java Iterator Interface. It starts by defining a stack of expression trees that will be used to be able to do a non-recursive traversal of a tree in pre-order. Its constructor takes the root of an expression tree, and assuming that that root is not null, it pushes that root onto the stack. So now we have one element on the stack. As you may recall, there are several methods that are part of the Java Iterator Interface. Let's talk about the simplest ones first. Here's the hasNext method. As you can see, hasNext simply checks to see if the stack is empty or not. If the stack is empty, then it doesn't have a next. If the stack is not empty, it does have a next. There's also a remove method, which is used to remove the element that was most recently iterated over. In this case, we just pop the element off the stack to remove it. The bulk of the actual processing is done in the next method. The next method is used to retrieve the next element and also advance the iterator. Here's next. You can see it. It's actually not that long. It actually has more comments than it does code. When next gets called, it first starts off by peeking at the top of the stack and stashing this away, the value away. This will actually be the result that's returned as the next element in the traversal. If the stack is not empty, the next thing we're going to do is we're going to go ahead and pop off the top element of the stack, which we just returned, or we actually stored it earlier. We're going to return that as the value. We have to get rid of it now so we don't revisit it later. And then if that top element of the stack has a left or a right child, we go ahead and we push those left or right children onto the stack so that the next time through the iterator will have something to work on. So we're basically getting back the value and we're also advancing the iterator by one. So as you can see here, pretty straightforward implementation. When we talk about the strategy pattern, we'll come back and look at some of the other implementations we have for iterators, some of which are not quite as easy to understand as pre-order iterator. Now that we've looked at the way that we implement the iterator pattern in Java, let's continue on with our analysis of the consequences of applying this pattern. There's a number of benefits that come. One thing that's real clear, hopefully, is that iterator makes the solution much more flexible. The aggregate and the traversal objects are decoupled, and they can co-evolve independently and separately from each other. For example, adding new traversal algorithms shouldn't affect the way in which the expression tree elements are stored or accessed. Likewise, adding new subclasses of composite binary node or other types of subclasses of component node shouldn't affect the iterators. These two things are relatively independent of each other. We simply have to make sure our implementation works properly, but we haven't tightly coupled them. Another benefit of using Iterator is the ability to support multiple iterators and multiple traversal algorithms. You might want to have multiple traversals taking place on a single expression tree, perhaps over different parts of the expression tree, perhaps in different traversal orders, in order versus pre-order versus post-order, and so on. And all those things can be supported by using this pattern properly. In the next video, we'll talk about how we can apply the strategy pattern to support multiple different traversal algorithms, looking at the tree in different ways. There are, of course, some potential downsides of using this pattern, one of which is overhead. So there's obviously additional communication required between the iterator and the aggregate it's iterating over. For most standalone systems, this is not really a big deal. It's the overhead of a method call or two, perhaps. When you start trying to use iterators in concurrent or distributed systems, however, this overhead can become significant. If there's a distribution boundary or a process boundary or concurrency involved, then the amount of time required to go across those boundaries can be problematic. We'll talk about ways to get around this problem when we discuss the implementation. Another potential downside with the pattern are the dependencies between the iterator implementation and the aggregate implementation. For example, if we add a new subclass to our composite, say composite ternary node, then that may affect the way in which the iterators have to be implemented. They probably have to take into account that additional piece of information that they would use. Now, it's not a big change, but it's going to require some modification to the iterators themselves. There's also the issue from an implementation point of view of a number of different considerations. For example, when we start to implement an iterator, we have to decide what style of iterator do we want to follow. For example, the Java version of Iterator is not quite identical to the Gang of 4 version of Iterator. It's somewhat similar. As you can see here, we have a way to create an iterator, and once we've got it, we can advance through it using hasNext and so on. But there are also some other issues as well. Here's an example of illustrating how the Gang of Four style iterators work. In this particular example, there's a few extra methods and basically the same idea, but this is a little bit different. More radically different is the way in which C++ iterators work versus the Gang of Four and Java iterators. C++ iterators are somewhat different. They have so-called value semantics, and so there's some additional effort required to implement them. The way that they work is also a little bit different, but it's basically the same idea. It's certainly the same pattern, but the realization in C++ is not quite the same as it is with the Gang of Four or Java. This becomes more obvious if you try to implement Gang of Four style iterators in C++ versus using STL iterators in C++. The STL iterators are more complicated to implement, but they have some desirable properties in terms of managing state and managing memory and memory life cycles. There are a number of other implementation considerations as well. There's trade-offs between internal versus external iterators. The Java iterators, the C++ iterators are typically external, which means that the state of the iterator does not reside within the aggregate that's being iterated over. It is interesting to note that in Java, if you inherit from iterable, then you can actually implement an internal iterator, which has all the pros and cons that we talk about internal versus external. It's more limited, but it's also easier to use because you can combine it with the for each loop in Java to iterate seamlessly without having to even use the iterator, factory methods, and so on in your application code. Other implementation considerations, making sure you don't violate the structure of the aggregate, making sure that you try as much as possible to keep those things decoupled. The temptation, if you're programming a language like C++, it has friends, is to make the aggregate and the iterators friends, which has some downsides in terms of coupling. Another interesting design consideration is robust iterators. So robust iterators allow you to be able to make changes to the underlying aggregate without affecting the iterators that are already iterating over that aggregate. Not surprisingly, that is a lot more complicated to implement and takes more overhead to implement properly as well. Some other implementation considerations, trying to minimize synchronization overhead in multi-threaded programs, trying to minimize latency overhead in distributed programs. A common approach people often use in those environments is to apply something that's a pattern compound called batch iterator, where you combine the concept of iterator that gets you things back without exposing implementation with the concept of batching. And what you typically do is you have an iterator give you back a batch of elements that can be iterated over locally, and when that batch is done, then you go back and ask for the next batch from the iterator. And this is a nice way of being able to minimize latency in concurrent and network and distributed applications. There's a number of known uses. Iterator is a very commonly used pattern. It's used a lot in languages like C++ and Java and C#. It's also used for things like C buffered I/O. The various buffered I/O mechanisms use iterators of forms with things like getC and putC and so on. It's obviously built into the JDK. The interface iterator we were looking at before is part of that. C++ range-based for loops and Java for loops we'll talk about in a second. Those are examples of how we take things that are patterns and transform them into language features. In fact, this issue of iterator pattern becoming a language feature is actually a recurring theme throughout the history of computing. In general, patterns that are useful in one generation of programming often evolve into programming language features in subsequent generations. For example, if you were to go back and take a look at how assembly language programmers in the early days of computing structured their assembly code, you would find that they used patterns of assembly programming that later found themselves into language features in second-generation languages like Fortran and C. For example, the concept of a loop or a closed subroutine or a switch statement or an if statement and so on. Those were examples of things that used to be patterns in assembly code that found their way into language features in later languages. Still later, in the 70s and 80s, people began to take the patterns of information hiding and lead to language features in languages like Ada, C++, Modula 2, later on in Java, and so on, for encapsulating information in various ways. The concept of packages, namespaces, classes with public and private parts and protected parts and so on, so-called access control sections or access control specifiers. These were all things that started as patterns that later found their way into data abstraction features in languages. Likewise, people who were doing early C++ programming tended to use preprocessor style patterns to provide some type of template or generic scheme in the C++ language. And that became very useful, and so it found its way into C++ and later into Java in the form as parameterized types and generics and so on. And as we've been talking about here, iterator patterns in things like STL and in Java and C# later on lend themselves to find their way into language features in those languages. So you can have Java for each loops, C++ range-based for loops, and so on. I would not be surprised to see these trends continue. As more patterns come out, people will find ways to implement them and reify them, objectify them as programming language features. But always keep in mind that not all patterns lend themselves to programming language support. There are certain patterns that really spill out of any given language to implement. And a given language may not give you the full flexibility of a pattern feature, even if it happens to implement a variant or a portion of it. So to summarize this section, the iterator pattern is used to create objects that traverse the composite-based expression tree and access each of its elements one at a time. And we'll later combine iterator with some other patterns to further improve upon our application design.